Hello and welcome again to the course on Design and Pedagogy of the Introductory Programming course. This is the final lecture of the first part, Introduction and Survey. So the question that we are going to consider in this part is, will programming be easier in another programming paradigm? Programming paradigm basically means a model of computation and a language as well. But it means more a model of computation, and you will see what exactly I mean by a model of computation in a minute. The reason for asking this question is the hope that perhaps there is a simpler model of computation, that is a model of computation which is easier to understand and therefore which will enable students to program more easily. So as we have been seeing that programming seems to be really difficult, so it's worth looking at whether we can simplify it. And so people have tried doing this and people have looked at alternate models of computation. Here is what I'm going to do. I'm going to first talk about functional programming. Then I will talk about Dijkstra's approach. This is not so much a model of computation as it is a view of programming. How should programming really be taught? Then I will talk about object-oriented programming, and then I will talk about Logo and Scratch, and then I will conclude with a summary of this first part and list out the challenges. So let's begin with functional programming. In functional programming, a program is a mathematical expression. So just as 1 plus 2 is a mathematical expression, a program is pretty much like 1 plus 2. And execution is expression simplification. So if I have an expression 1 plus 2, I simplify it and make it 3. So something is changing, something is evolving, and that is exactly captured in functional programming, and that is thought of as an execution of a program. Functional programming can be done by using several languages, and only one such language is the scheme language. Scheme language is described in a really nice book by Abelson and Sussman, written in '96. It's a beautiful book, and I'm going to use this notation. In this notation that the scheme language represents, expressions must be represented in prefix syntax. So prefix means the operators must come first, followed by the operands. So operator followed by operands enclosed in parentheses, or function name followed by arguments enclosed in parentheses. So here, for example, is an expression. So this expression is to be read as sum of 5 and 3 multiplied by the difference of 7 and 4. So plus is an operator over here, and these are the operands. And the result of this and the result of this are multiplied together. Okay, so what do we do with this? The basic idea is we are going to simplify wherever possible. So for example, plus 5, 3 can be simplified to 8. So in that case, the entire expression now changes and it becomes times 8 minus 7, 4. So this is to be thought of as execution. We are doing computation and we are executing, and the expression is changing. So in fact, you can think of it as we have a program that has been given to us and we sort of keep on simplifying that program. Then this expression in turn can become star 8, 3 because 7 minus 4 is 3. And then that becomes 24 because 8 times 3 is 24. And this 24 is the result of that entire program. So as you can see, evaluation is something that you already know. A program is something that you already know. And therefore, this is considered to be a really attractive model of how to describe programs. Of course, this is not all there is to it. So two things I need to tell you more. So programs can contain names denoting values as well as functions. So wherever there is a name, it is replaced by the definition. So if there is a name denoting a value, the value will replace that name. If it's a name denoting a function, then the function definition is substituted in place of the name whenever needed. And of course, if it's a function definition, then the argument values replace parameters during substitution. So we'll see an example of this right away. Here is a more complex scheme expressional program. So this program is just a definition, but let us read it first. This is an expression which defines a function. Fact is the name of the function. It takes one argument n and it is supposed to compute the factorial. Inside it, there is an expression if. There is the if function. So what does the if function do? If function has three parts to it. The first is the test, the next is the consequent, and then the last is the alternate. So for example, in this if, this part is the test. Okay, this test is going to check, is n equal to 1? This part is the consequent, and this part is the alternate. So if n is equal to 1, then this entire expression represented by the if statement is going to be this entire expression is going to be resulting in 1. If n is not equal to 1, then this entire expression is going to be resulting in this expression. Okay? So let us see now how an expression which calls the factorial function will execute. So suppose we have written down an expression fact of 2. What happens? So as we said in the last slide, the name fact is going to be replaced by the definition of fact, and 2 is the argument, and 2 will replace the parameter in the function. So this will become, so this entire function body is going to be placed over here. So notice that n is 2, so if instead of if equal to n1, we will write equal to 2, 1. So 1 is going to come as such, and then times n fact of minus n1, so everywhere n is going to be replaced by 2. Okay, now this expression that we started off with has now become this expression. It looks longer, but actually it is simpler because we have substituted for a definition. What happens next? Well, the idea is that wherever we can simplify, we will. So for example, in this case, we can simplify this expression. Is 2 equal to 1? So it is not equal to 1. So which means we can simplify this entire expression. So if this 2 is not equal to 1, then it will evaluate to the alternate. So it will evaluate to this. So as a result, this big expression will become just the alternate, which is over here. Now in this, can we evaluate anything? Well, we cannot. So therefore, we will substitute for fact of 1. So fact of 1 again will go back to the definition and will put the body of the function inside this. So this will be our new expression. We are going to have n, this n is going to have the value 1 because we called fact with 1. So our expression is going to be if equal to 1, 1. Okay. So there should be a parenthesis over here, checking equal to 1, 1, then it should be a 1, otherwise it should be this expression. Now we can easily check that equal to 1, 1 is true, and therefore this time the consequent is returned as the result. So our new result is going to be times 2, 1. So this now can be evaluated and it has become 2. So you see what is going on? We have expressions and we are only simplifying the expressions, and of course we are substituting for function definitions wherever we need it, but all those seem like standard mathematical operations. All those seem like students already know this. So the hope over here is that since students already know simplification of expressions, they will be able to understand programs, or they will be able to even write programs in a much more easy fashion. So first remark which I just made, functional programming executional model is very simple and familiar, expression simplification. Its syntax is very simple, expression syntax. And here is one more interesting point, that it is often very easy to reason about functional programming programs, so scheme programs for example. Because just as in mathematics, the value of a name never changes, even here, if I have a name n, it always means the same thing. Well, in a different context it might mean something different, but within a given context, I cannot do anything like I equal to I plus 1. So whenever I see n, I know exactly what it is referring to. So this is another idea which is considered to be easy, to make functional programming easy. Functional programming uses recursion heavily. In fact, there is no iteration as such. Recursion is sort of the standard way in which iterative actions happen. You may note that we can always use recursion to implement iteration, though not exactly vice versa. So in any case, in functional programming, we use recursion, and very often it corresponds to whatever happens in mathematics. Many mathematical definitions use induction. So many definitions are inductive, and functional programming correspondingly uses recursion. Now, recursion is maybe very natural, but recursion can also be a little bit tricky to understand. Many programs written using functional programming are very, very elegant. They can often be very small, very compact. Okay? However, there are some classes of programs where this notion of just using recursion becomes very tricky. Or the idea that we do not change the value of a variable becomes very tricky. So for example, if you are doing depth first search on graphs, it is quite hard to express this using functional programming. Finally, it should be noted that imperative programs are usually much faster in practice. So what do we conclude, and what has the field concluded? So functional programming is not accepted worldwide. It doesn't have that much acceptance, but there are some very, very strong proponents. So what we can say is that we have learned something valuable about programming when we study functional programming, and we should perhaps be using those principles whenever possible. So what are those principles? So we should not be using global variables. So the idea here is like what has been mentioned above, that we want to make it easy to understand programs. So then if we have a name, we should expect that name to have the same value everywhere. If you have a global variable, then a function call can change the value of a global variable. And so we should avoid it. So whenever we write a statement like I equals I plus 1, we should regard that as a potential mental overhead. So I equal to I plus 1 is not possible in functional programming, and that's because that imposes a mental overhead, and we should even avoid things like this, and global variables are sort of a very strong example of that, where the name for which we thought a certain value was assigned suddenly changes, and especially if the change is happening inside some other function, it is very, very difficult to understand what is going on. Functional programming also encourages functions themselves to be passed as arguments. In fact, functional programming doesn't make a distinction between functions and variables. The term used over here is that functions are first-class citizens. Early programming languages, early popular programming languages had a very, very big distinction between functions and ordinary variables. But now things are changing, and ideas like higher order functions, which sort of evolved in functional programming, are now coming into standard programming languages. So for example, the lambda expression, which is an important idea that arises in functional programming, which I have not had the time to go through, but this idea has been inducted into C++, Java and other standard programming languages. So what we are going to say is, and how we are going to proceed, is that we are not really going to use functional programming, but wherever possible, we will try to use functional programming principles. So if it makes sense, we will remember that we can pass a function. We can pass different functions as arguments to another function. And inside that function, the function that we pass might get called. Or we might make sure that we don't use global variables. So these are some of the lessons that we can take away from functional programming, but we are not going to use functional programming. We are not going to change over to functional programming. Next, we will discuss an approach due to Dijkstra. This is not quite a programming model, but it's an approach in which Dijkstra says that proving the correctness of programs is extremely important, and also deriving complete programs. So the idea over here is, you are given the statement of the problem, you decide what values you need to calculate, and then you say, okay, if I want to calculate these values, well, then I must have these values. Or if I have these values, I can calculate these values. And you step by step, in a logical fashion, you decide what you can calculate, what needs to be calculated, and if the two meet, if what you can calculate and what needs to be calculated at some point become equal, then you have a program. But the idea is that at each step, you have a proof that if I can calculate this, I can calculate this next thing, or if I need to calculate this, it suffices if I calculate this. So at every point you have a proof. Now, simple loop-based programs are derived, and recursion is not considered so much in this approach. But there are variations on this approach, or there is work which looks at recursion as well. And this approach can be considered successful in the sense that just by reasoning in this manner and sticking to having proofs for whatever you do, you can often derive quite tricky and fast algorithms. So O of n time, linear time algorithms are derived for problems in which simple algorithms might give you n squared time. Unfortunately, the kind of logical manipulation that is required in this approach tends to be a little bit cumbersome, and beginners find it dry. And this is probably the reason that this approach has not caught on. So what is it that we conclude from this? Well, we believe that basic notions such as invariants are important even in introductory programming. So invariants are a very, very strong idea that comes out of Dijkstra's approach, and we feel that that is important. However, we don't want to go all the way and only derive programs or prove everything about a program very, very formally. Okay? So what we are going to take away from Dijkstra's approach, that we should be stressing invariants when we talk about even about introductory programming. But perhaps other steps could be left informal. And Dijkstra's approach is often about deriving very clever algorithms. And clever algorithms perhaps should not be expected in introductory programming. What I mean by that is, we should not really expect beginners to derive clever algorithms. Because clever algorithms, well, requires cleverness, and often we tend to think of cleverness as something that happens in a second. But before it happens in a second, you need to have experience, and you need to spend some time so that you develop the intuition to generate clever algorithms. And there is just not enough time in the introductory programming course that we should be stressing clever algorithms. A very common approach is the object-first approach. Object-oriented programming is arguably the most dominant programming paradigm today. Now, proponents of this paradigm believe that it should be taught from day one. Okay? Why? Because otherwise you might get corrupted by other approaches. Books have been written about this and about teaching object-oriented programming, and typically, not always, the application domains considered in these books are things like designing user interfaces, drawing pictures on screen. Okay? And for whatever reasons, this paradigm tends to be heavy on syntax. Okay? It often appears to give undue importance to minor issues. How do you change the color of a text box? This is of course not an inherent aspect of object-oriented programming. But somehow when it is taught to novices, these are the issues that get importance. However, there are many concerns. So, in some sense, object-oriented programming is not an alternative paradigm for something like C-based programming or the so-called imperative style programming. It is something in addition to introductory programming. Or to put it more directly, how can you learn member functions without learning ordinary functions? Aren't member functions necessarily more complicated than ordinary functions? So in member functions, there is a privileged argument. There is sort of a special argument, which is the object on which you are invoking the function. There is no such special or privileged argument in ordinary functions. So to that extent, ordinary functions are easier. So when we talk to beginners, shouldn't we be teaching them ordinary functions first before they can be expected to understand member functions? In general, object-oriented programming proponents say that it gives a more natural view of the world. However, there are research papers, and I have mentioned one due to Detien over here, which have done surveys and studies on students, and they cast some suspicion or aspersions on whether object-oriented programming lives up to its promise. So what is our conclusion? Well, we think that object-oriented programming is strictly harder. Even if it is useful, it is strictly harder. And since we seem to be in a crisis situation, let us not make things more difficult for our students. Let us first make sure that they understand ordinary functions and ordinary programming before we get into objects and all the issues related to objects. Okay, the last programming paradigm that I want to survey is the so-called logo and scratch paradigm. Again, it's not a paradigm as such, but it's a bunch of projects or programs that have been developed very, very systematically, if I may say so, for teaching programming to children. Logo has been developed by Papert and several others, and Scratch by Resnick and several others. And Scratch actually could be said to be a derivative of Logo, and Scratch is not the only derivative. There are other derivatives also. What does Logo do? So Logo, first of all, teaches programming using graphics and geometry. Graphics and geometry grabs attention. Children and even older students love to see pictures, and especially pictures that are being drawn or pictures that are moving or being manipulated. Okay? There are two paradigms actually. There are two ways in which Logo and Scratch get used. The first paradigm might be called the narrative paradigm. What happens here? Well, in this, students create graphical characters, or they may have they may use pre-created graphical characters, and they animate or choreograph the movements of the characters, and they use this to tell a story. So a program will essentially be a script. So the program might say, move this fairy from this tree to this house or something like that. Okay? So in each step of the program, you are going to do something to the characters and something will happen on the screen. So you are programming these characters on the screen, and they may do things on the screen that they, for example, they may draw lines on the screen as they move, for example. Scratch is especially beautifully crafted, and in fact, people who have artistic talent, students who have artistic talent, can create their own graphical characters. Of course, this is an expression of graphical talent, and many may say that, look, what is the programming in this? And they might indeed be right. But the creators of Scratch say that the point of Scratch is to bring artistically talented people into programming, somehow or the other, not fully, but at least partially, so that they start using programming. Not sort of the kind of mathematical programming that we might want, but at least they start moving things on the screen. And once they start moving things on the screen, they may want to do other things. Say, for example, they may want their characters to walk. So that means maybe they have to put some kind of a loop over there. Okay? So it may or may not encourage students to learn the full range of programming. To give an analogy, and only an analogy, it's somewhat like web page design. So you are laying things out on the screen, and if I click on this, you want this to happen, you are sort of setting things up. And maybe you are not writing programs in which you need to worry about whether there is termination or not, whether the program runs in linear time or not. Those are things which may not get tested, or you may not need to understand those things when you write narrative programs. The second paradigm is the more general paradigm, and even in this, graphics plays a role. But in this case, the graphics is meant to be much more precise. You are drawing patterns which might have intricate features, but there may be symmetry, and so you might have to reason about that symmetry, and you might have to program that symmetry. And of course, the language is large enough so that you can solve standard programming problems. Actually, the language is large enough, in fact, so that you can also do things like parallel programming to a little bit. Logo and Scratch are very successful in that they encourage children to program. Okay, so they have created the hope or the confidence that children can program. However, it must be said that their strength is, in my opinion, is slightly different. I don't believe that they have been successful in helping every child to program. What they have been successful in is that they have provided an avenue for children who have inclination to program to come out and start programming. It is not clear that they can inspire every child. They have tried to do so by bringing in this narrative model, and some additional people have come in, but again, will they be able to program in the sense that we want, where they have to reason about termination and things like that? It is not clear. However, the main takeaway, in my opinion, from Scratch and Logo is that they build on what students know and like. Students like graphics. Students have learned geometry. So students like using what they have learned, and that is what Logo as well as Scratch beautifully exploits. And it also shows this general idea that geometry is actually extremely rich. When we look at pictures, of course we can see iteration, we can see repeated patterns, but not only that. We have pictures in which there is recursion, there is recursive substructure, and we can write recursive programs. And in fact, you can write recursive programs in Logo which are very easy to understand. So I think those are the conclusions that we should take away, and we should think of exploiting geometry as a means to teach programming. Another idea which has come out of Logo, so to say, is the idea of scaffolding. So consider the following two assignments and tell me for yourself which is more exciting. Okay, the first assignment is write a program to multiply two polynomials, and the second assignment is program this robot so that it dances. This is hardly a fair question, right? 90% of the people will say, of course, I want to program the robot. I mean, that is so much more exciting. Well, it might be exciting, but for example, it requires you to learn robotics. And second, making a robot dance requires a lot of code. So what do we do? Well, here is the idea. So in our introductory programming course itself, we may think of teaching some domain-specific concepts. So maybe we teach a little bit of robotics. And then we provide the code which will do, say, the high-level functions. So maybe we will provide the code which makes a robot walk. And then we'll tell the student, oh, now you change the code so that instead of walking, the robot dances. So this way, we are providing additional material so that the student gets drawn into this task of programming. So if you have seen buildings being built or repaired, a temporary structure is often erected on the outside, typically made of wooden planks or metal poles and things like that, and it is used by workmen while building or repairing or cleaning the building. And that structure is called scaffolding. So we are going to provide code which will be used by students not because they need to learn that code, because that code will make it easier or more attractive for the students to learn programming. So people have used this idea in many subjects, and scaffolding has been developed for many, many domains: robotics, data science, graphics, geographical information systems, and even some others. So this seems like a really nice idea, but we have to worry about two things. First of all, if students are going to use robotics as scaffolding, they need to learn robotics. So if we are saying that programming is already too difficult, we have to ask the question, is it going to be more difficult because students need to learn robotics? For some students, it certainly will be. And some students might like robotics, some students might like data science, some students might like geographical information systems. But if we teach only one of them, we might be leaving out some students. We might be trying to teach geographical information systems to students who wanted to learn robotics. So scaffolding might be a good idea, but we have to be careful in using it. Okay, so now I am going to summarize the first part of this course, and let us go over what we have learned. So first of all, it is important to remember that worldwide failure rates in programming courses are high. The Indian situation appears similar, and quite possibly the failure rates may not be high in India, but that's only because our exams typically are much less demanding. But it is not at all the case that our students are being trained better than what is happening worldwide. So we really should be considering what is going on to be a crisis. The main disappointment of teachers seems to be that students are not able to write programs to solve simple, unseen problems. Our hope is that students will learn programming and then they will use it just as they use arithmetic or writing. It will be an extension of their thinking abilities. But that doesn't seem to be happening. If we give them a new program, a new problem, students are finding it very difficult to write programs to solve those problems. And courses seem to be saying that, look, they should be able to solve simple problems, but we are at a loss to provide a definition of what a simple problem is. So perhaps we should be doing that. We should be thinking carefully about what kinds of problems should we be asking. Okay. Experts have given tests of widely varying difficulty to test programming aptitude of students. Okay. So does it mean that there is no consensus about what programming is? Okay. Or does it mean the experts are lowering standards in light of student performance? So this is on one hand as far as teaching programming to college graduates is concerned. But there is lots of excitement about teaching programming to children. Okay. So perhaps this is because children are given simpler problems, okay, and perhaps graphics and animation provide good motivation. But maybe we should be thinking from these lessons, thinking from this experience as to what we can do when we teach to college students. We have seen that few approaches worry about formal correctness, but we think that they are important. And there is confusion about how to or whether to or how much to teach algorithm design, also problem solving. We are relying on some kind of street smartness, but we really should be quantifying or specifying that a little bit more clearly. All right, so to conclude, let me just go back to a slide which I showed earlier, and let me say that the questions raised in that slide still remain. So what are the questions? Is programming so hard? It was conjectured that it is hard, and we have not really seen evidence to the contrary. Do we need to slow down our courses? Well, we don't yet know. We need to think about it. Should we teach differently? Well, it appears that we don't really teach how to design programs, how to deal with unseen problems. So something needs to happen on that count. Are we able to motivate students to study? The piece of good news is that graphics and animation seem to motivate children well, and maybe scaffolding can help. Okay. And finally, are our exams fair? So over time, the tests used by researchers for measuring programming competency seem to have become easier. However, this really means that we don't know what is a fair test. We seem to be wavering about that. And my personal experience is that if you look at large number of examinations, you will find suddenly there is a hard problem. Suddenly teachers feel compelled to give hard problems. So there is, in my mind, there is some question about what is a fair exam, a fair examination, a fair programming problem for first year students, and what is not. So all these questions need to be studied, we need to think about them, and that's what we are going to do in the following weeks. Thank you. We will stop over here.